Okay, so the next video here that I'd like to show you guys is the next equation is going to be this number 2. As you can see, it is an actually acceleration equation, just like number 1 is, except the A for acceleration is not here anywhere. And so let me explain that, why it is like that, okay? So the reason being it's like that is this, that technically we're going to use this equation right here. Let me undo that. And this one right here. And remember, this equation is for no acceleration, right? But we're going to use it anyway, and this is why. So we're going to solve for x, and then so we're going to times t on both sides, and t's cancel out right here, and we end up with, we got a t on this side. So we end up with delta x on one side, and then we get the v and the t on the other side. So I want to put v times t. And this, let's say a car or something, or a ball, whatever, is going to start at this speed, so we'll call it the original speed, and it speeds up, we're going to say it accelerates, until it reaches this new speed right here, and we'll just call it v, right? That's the final velocity, that's kind of where we're doing it, and VO is the starting speed, right? So it does change speeds, so it does accelerate, okay? So it does accelerate. But we're going to use this equation, even though this equation technically, to be honest with you, should not be used for, this is not for when something accelerates. But this is what we're going to do. What is this? What speed is this thing going at? Well, it started at this speed. And then ended at this speed. Okay. But what speed did it go at the whole time? Well, it changed all the time. That is true. But if we do something like this, we take the starting speed and the ending speed. And this is assuming that the acceleration was constant, of course. That's nice and linear. That's constantly speeding up evenly. That if we take the 2 and add them and divide it by 2, we get something like an average speed, the average speed. And if I know the average speed, I can actually just plug it in there and tell, and then if I know how much time it took to do this, I can tell how far it went. So the equation is, so what we're going to do is plug this in where this goes, and then we get delta x is equal to this stuff right here, VO plus V over 2, and then times t, right? Because then we don't forget about the t. And that should be it. Where is that thing? Yeah, that's it right there. They just put a parenthesis around it. So let me do that so it looks the same there. Do that stuff first, and then times it by t, and that'll tell you how far something goes when it changes speeds. So if it goes from one speed to another, we can use this equation. It's technically one of our acceleration equations. It just doesn't have any a anywhere. So if you have a problem where it asks you some information like how far did something go, and you know it's accelerating and stuff, but yet they don't give you a, so they don't give you the a at all, but you know it did accelerate and they don't give it to you, and they're not even asking it for you. They're not asking for acceleration, and they're not even giving it to you, but yet you know it did. This is the equation you're going to use, okay? So here's our sample problem real quick. A car accelerates from rest to 30 meters per second in 10 seconds. How far did it travel? So let's write down everything we know. That's rule number 1. So let's see, accelerates from rest. We know rest is a 0 to this. So it goes from this speed to this speed. So the starting speed is 0 meters per second. The final speed is 30 meters per second. And t is definitely 30 seconds, right? If you see a seconds or a minutes or anything, we know that's a time. How far did it go? So they're looking for a change in position. They want to know how far it moved. Then, of course, we're going to bring up the old equation and see which one has this stuff in it right here. So all you're going to do is look for which one has this. And this one has a delta x, right? And it has a VO and has a t. Perfect. T, but there's an a. So can't use it. I don't have acceleration. It is accelerating, yes. See, it does accelerate, right? It's accelerating or changing its speed from one thing to another, so it's definitely accelerating. But I can't use that one. And I can't use this one because it has an A, and that one can't use an A, and this first one has an A. Well, that's the only one I can use. And actually, do I have all that stuff? Yes, I do. This is a perfect match for my problem. So I'm going to use that equation, and the equation is this. Delta x, change in position, is equal to final initial minus final divided by 2, and then we times it by the time. So let's go delta x, plug them in. Starting speed is 0, plus the final speed is 30 divided by 2, and then we're going to times that all by the time, 10 seconds. I messed up here, didn't I? Good thing I caught that. You guys would have been all confused, right? You guys were probably thinking, I saw that. You probably did. So that's 10 seconds. There we go. So I plugged everything in correctly. I caught myself, luckily. I don't have to re-record this. What a waste of time that would be. I've done that a few times already. 30 divided by 2, just kind of solving that stuff, times by 10 is equal to delta x. That becomes 15 times 10, right? And I think you guys already know the answer. It's going to be 15 times 10, which is 150 meters. How do I know it's meters? Well, because we were in meters per second, you know? So this is the average speed. The average speed ends up being 15 meters per second on average. It started at 0, rest, and it ends up at 30, and on average, averages about 15, about halfway in between. That makes sense. And it did that for 10 seconds, so it's going to go 150 meters. There we go. And that's it, guys. So try a few practice problems. Remember, just be careful. Sometimes my practice problems are not going to all be starting at rest. Sometimes it will give you a speed there, okay?